Hi everyone, thanks for coming. And today we're going to talk about really exciting topic about how to stay curious, especially when you're working with databases. Somehow I see that nowadays it's really, well, people are totally pressed by the business and stuff. Yes, sometimes we just need to be curious, and sometimes we have to get this back feeling when you're hacking something and, get this excitement back. A little bit of a background. So I work for Zalando for some time already, and I'm a part of the team that basically runs all the database, all the Postgres databases in the company, and unfortunately it's a lot of them. In the meantime, I'm one of the contributors of Postgres, and you probably have heard about some of my contributions, like for example different JSON-B modification functions, or something from the recently, for example, pluggable storage support for PSQL and pgdump. And now a few words about why I got this idea about this presentation. So this situation that we have to run Postgres in many different environments. So we have to run Postgres in like data centers, relatively legacy data centers. We have to run it just purely on AWS and the cloud. We have to run it on the Kubernetes, of course, and all this stuff basically led me to the idea behind this presentation. That's approximately what we're doing. We basically have to do this. We have to run Postgres everywhere, and we are doing this fortunately by relatively successfully thanks to 2 open source projects that you can check it out. One called Patroni is super successful. It's like already 2,500 stars on GitHub with a lot of contributors, and it's basically our high availability solution for Postgres. And Postgres operator, which is basically our Kubernetes operator, because sometimes, in general, Patroni it's not enough to run this on top of Kubernetes, and we have to provide more information about this stuff. So and now let me explain what I'm going to talk about. So let's imagine we have a database. Well, in fact, somehow it happened in this presentation. If you will replace Postgres in this presentation, it will still make sense. So it's not only about Postgres, about database.
Good afternoon.
Good afternoon.
So let's start our talk about filtering system calls in Docker and Kubernetes, and also about filtering system calls in general. Who am I? I work for Strato, which is a part of 1&1 Ionos, and I've basically been working with Linux since forever. Have been stumbling about every corner of that thing, and today it's about system calls and filtering. So what are we going to talk about today? The first question, of course, is what is a system call? I will actually spend quite some time on this one. It deserves some attention, but if you already know this, you can safely go to sleep for that part. I'll try to wake you up after. Then is why would we filter system calls? Which calls? And then how? Calls. In general. So the general case for Linux processes, and then how to do it in Docker, and how to do that same thing again in Kubernetes.
Yeah, sorry for that. We'll just wait a bit.
All right, so let's start with the first one. What exactly is a system call? System calls are how processes, how software talks to the Linux kernel.
Not yet.
So a system call is more or less the API of the kernel. Whenever you want the kernel to do something for you in your process, you call a system call.
It's actually really funny because I
want basically
to talk,
that means you have to, because you can't do much without system calls.
To listen to
Whenever you call the system or execute a system call, what happens internally is that the execution domain, the mode of operation of your software is switched from user mode, where your software is executed, to kernel mode, where you can only have certain functions work for you in kernel mode with your parameters. And after that, when the function is called and it has done its work, it will go back.
So are we good? Yep, can you hear me? Yes. Perfect, thank you. Thanks a lot. Not a problem, that was funny. I've never had this experience before, so it's something interesting, something definitely that I will talk about in the future, maybe like funny story, one of those. So let's return to, well, that was about, I guess, this seccomp stuff and system calls. Let's return to databases. what I was trying to tell about. So let's imagine we have a PostgreSQL in our system, doesn't matter, cluster, whatever. And let's imagine you want to realize, you want to understand what's going on. Normally, it's not a problem. You're just going to check pgstat something. There are a lot of information that Postgres by itself can provide you: pgstat activity, statement, logs, database information, user tables, whatever, a lot of it. And that's like normal, I don't know, 90% of time it's actually enough, and people are actually satisfied with this information. But there is a problem here. There is a limitation in a sense that this information can give you an impression only about what's going on in the database from the Postgres itself, from the Postgres point of view, or also plus some description about the data you store there. Now, we suddenly realize, okay, but we run database not just like in the vacuum, right? We run it on top of some operating system, and obviously, like the whole system itself, we have to somehow monitor it in general, right? Usually people think about this, they scratch their head, they're saying, okay, let's try to monitor something global. I don't know, CPU saturation, I/O utilization, something like that. And now suddenly we realize, okay, we're going deeper. It's not only an operating system right now, we run inside some system, inside some control group, C group, so within a container, Docker, or whatever. And it's another level of complexity that we have in our system. And obviously, we also have to monitor it somehow. People already at this point started to scratch their head. They have no idea. They're going to read some outdated blog post or something like that. Maybe they can come up eventually with some solution, but here is already some problems. But then suddenly we realize that it's not only a container, we also run this on top of like some virtual machine, yeah, in the cloud. It happens quite often, unfortunately, which contributes even more complexity at this moment. And then eventually, as a paramount of this whole system, this virtual machine was actually like one of the nodes of our Kubernetes cluster. At this point, people are completely lost. They have no idea what's going on. Well, besides first two layers probably. And every time when something happens, like some problem, performance issue, like some blurb on the performance graph in Grafana or something, people usually are doing something like that. They're saying, okay, we are serious business. We don't have enough time to investigate this, which is a really terrible mistake as for me. They're saying that we don't have time to go to the low-level details. Let's just reboot our database server, or maybe scale it up or something the best I've heard so far is that it's like open source project, they have to fix it, not us. It happens unfortunately, and at this point, as for me, why it's wrong, people first of all, they're losing really important knowledge for themselves and for the community of the project they're using. And the second, most of the time, unfortunately, of course, this error comes back. And that's why in many talks, unfortunately, we see many times that people are saying that's some normal performance problems. We see it every now and then, some blurbs, and we just ignore it. So, at least my position about this is that we have to go a little bit more inside to figure out what actually is going on. Maybe, it will be a little bit longer, but it will give you a lot of interesting knowledge and just fun. So, if you expect the plan for this presentation, I have to disappoint you. There is no plan, unfortunately. This presentation is basically just a collection of different interesting use cases, that I found interesting or at least useful. And those use cases, basically, they're talking about when there is an issue that you cannot troubleshoot from the Postgres within the Postgres itself. You have to take a step back, take a deep breath, and deploy some different tools. Maybe think a little bit outside of the box, and in general, extend your area of knowledge and the tools you're using to get more information. So, if we're talking about getting a little bit more information from not only the Postgres itself, but from the system, what I'm talking here about. First of all, it's probably most underrated and underestimated information source is a source code of the project you're using. If we're talking, for example, about Postgres, I really encourage you to go and read the Postgres source code, because it's amazingly annotated and documented, and all the commentaries that really make sense. I mean, I've got this experience in my own practice that we managed to solve some issues by reading the source code instead of documentation, because, it happens that documentation is a little bit more dry and not that good, provide not that good coverage, unfortunately. With the Linux kernel, for example, it's a little bit different beast, of course, but at the same time, all the new stuff, IO ring, C group version 2 and stuff, it actually also comes really nicely written and with a lot of documentation. The second source information sources, basically tools that a lot of people, mostly about DevOps, are aware about. It's like strace, GDB not that much in this presentation, but in general too, and perf. The third one, for your information, here we're concentrating on the Linux-based distributive, so because for BSD you use dtrace or something and you're already good. So yeah, for Linux we also have different virtual file system, and we can get a lot of information from procfs, sysfs and stuff, and the last part we're going to talk about such popular buzzwords as BPF, extended BPF and stuff. So let's go immediately to the first interesting use case. Let's imagine you have a reasonably modern version of Postgres. You run some analytical queries, and instead of like a result of your query, you've got this error: could not resize shared memory, blah, blah, blah. It's kind of a scary by default because it's like an error, right? You do not expect that many errors from Postgres. It's super stable. So, and the problem is that obviously you can't really troubleshoot it from the Postgres itself. How? So how to solve this problem? Actually, it's super straightforward. We take a strace. For those of you who don't know, a strace is basically a really amazing tool that allows you to figure out what kind of system calls your application is doing. Plus, there is a switch -k, not that many people somehow knows about this, that allows us also to see the full back trace via lib unwind that led to this particular system call. So what we're doing, we're going to attach to our backend for Postgres our strace, and we see immediately what's going on. So yeah, indeed, we try to get some shared memory segment, dynamic segment. We try to truncate it and then allocate it, because basically truncate and allocation means that we're trying to create a new one. And then indeed, instead of getting a success result code, we're getting -1. And here we can see the stack trace that led to this allocation. And here we can see immediately what's the problem. The problem is now all the things are actually starting to fit into one picture. So we see that here what Postgres was trying to do, it was trying to execute something in parallel. We know that starting from Postgres 10, 11 stuff, about these versions, parallel workers are really started to be super useful. And now we remember that we were doing some analytical queries. Most likely Postgres was running a lot of parallel backends, parallel workers. And yeah, for every parallel worker, we have to have a special, separate dynamic segment. And the last point in this equation is that when it happens only when you run in Docker. Why? Because in Docker, there is a by default limitation, obviously, that the FSHM can be max 64 megabytes. Of course, it's configurable, but it's a default value. I know that many people knows about it, and obviously 64 megabytes, sometimes it's not enough for huge analytical queries, and here we are. So, you may say, okay, it's a cheat, because it was kind of a problem issue, and obviously you cannot troubleshoot some issues from the application itself, right? So here's an example of using strace for something more performance related. So there is a such thingy called VDSO, Virtual Dynamic Shared Objects. It's basically a functionality in Linux kernel that allows us to do really cool stuff. It allows us to execute some limited amount of functionality that normally belongs to the kernel itself without actually switching to the kernel space. Normally we're talking about, for example, functions like get, like time-related functions like get time of the day or something, which means what does it mean for us? This feature provides us a really nice performance boost because we don't have to switch from user space to kernel space, and obviously this switch always means an overhead. And you would be surprised how actually often, not only Postgres, a lot of databases are doing this time-specific system calls a lot, because basically database for all the logins and stuff, database have to be aware about the timeline, right? So now let's imagine, the problem is that this virtual data VDSO feature, unfortunately, is not supported by some of the hypervisors. That's like a small tricky feature about this stuff. And most notoriously, it does not support it, for example, by Xen hypervisor. They are working right now on this thingy, and right now, as far as I remember, there are patches about this, but I'm not aware if it was already like merged or something. So now let's imagine we have a situation. We have, for example, some AWS cloud, some instances fleet in there, and we have a, like, for example, Kubernetes cluster that runs on the mixture of M4 generation and M5 generations. And if you know, M5 generation on AWS runs on this kind of a KVM hypervisor and M4 on Xen. So we have this distinction: on one we have support, on another we don't. And we see, for example, that we have like, I don't know, one master runs on some of the nodes and it runs slowly, then on another one. How do we figure out if this problem is actually affecting us? Straightforward. Again, we're taking a strace, we're attaching to our backend, and then every time when we see a real function call, something time related, it means that we're doing this overhead. It means that every time we switch into the kernel, and so on and so forth. So that's we figure out this problem. Okay, somehow it happened that I've I was doing this talk a lot over this year, and that's why I had to change the date in the last moments. And usually at this point I was talking about like CPU migrations and scheduling. If we will have time, maybe I will cover this too, but in general I decided that it's not interesting anymore, especially since, like, I don't know, starting from the September or something from the autumn, we have something more interesting to talk about, namely it's called memory, I think, data sampling, but I'm not sure. Every time I'm forgetting what this abbreviation stands for, but it's basically another nice vulnerability, one of those hardware vulnerabilities like Spectral Meltdown from the last year. Nowadays, like, it's so many already of them that people do not really notice them, but we have it already. And the problem is that obviously there is a vulnerability mitigation in Linux kernel, and obviously this mitigation means an overhead for us. It means that we're going to be slower, right? So now let's imagine the situation. We have a database, and we have the database runs on top of inside some virtual machine, and we know about this vulnerability. How are we going to figure out whether we are strongly affected by this or not? Because there are people who were actually reporting like 40% of slowdown or something like that for databases. Actually, we can do a little bit of a hack. Basically what I'm saying here, I'm just repeating. It's not my own research. I'm just repeating after Anders Voigt, who did a really nice overview of this vulnerability. But nevertheless, let's go through this. So, unfortunately, it's already not enough here to use just a strace. A strace is pretty simple. What we have to do here, we have to deploy perf and basically start to profile, to sample our application to see what's going on. Now, let's imagine that we were sampling our Postgres under the normal workload before this vulnerability mitigation and afterwards. And here, for example, we have this profile that we've got after this mitigation was applied. What can we see here when we compare both situations is that suddenly we started 25% of the samples are taken by this function do system call 64, which was not the case before. So it's already suspicious, right? It's something that's really strange. We can't really explain it. Why is that? And then we can zoom in with perf, and now all the things are actually start to fit again into the same, into the bigger picture. So we have this instruction here called verify W. And if we're going to read the documentation, if we're going to read the, basically report about this vulnerability mitigation, we can figure out that the mitigation itself was basically implemented in a way that in microcode for this instruction was overridden. And before this instruction was doing something totally useless, verifying some buffers and so on. It was totally unnoticeable. But now this function actually does what it does. It flushes all the CPU buffers to mitigate this vulnerability problem. And that's why we spend so much time on it. And that's we immediately see this problem, and then we can, for example, figure out via this, for example, proportion between the whole samples and the proportion of the samples that we're doing in this instruction, how much do we affected by this problem, right? By the way, when you're doing this, you have to be aware there is such thing as a skid when you're doing profiling, so that, for example, sometimes this number could be attributed, for example, to the next instruction. So here you either have to increase the precision, or, there could be some different situations. You just have to be aware that it doesn't really make sense that pop, for example, takes so much time. Yeah, so you just have to apply your common sense. And another thing, really interesting stuff. What we've noticed, that's actually how we've noticed that something is strange. We've noticed that somehow native safe hold for us is taking an incredible amount of time, although the database is really busy. Normally, if you see this stuff in a profile, it means that your database is not doing anything. It's basically like a swapper process that's basically idling, yeah? But it doesn't really matter if database was like fully utilized and like we're doing 30% of time nothing. That's really strange. And then, indeed, we're going to go to check this function out, and then indeed we see that we have also this mitigation inside. So here we are. Okay, another really interesting example of application of profiling, and why is it important, it's virtual machines. In particularly, something called log holder and log preemption problem. Log waiter preemption problem. This problem is so significant, so big, that there are some scientific white papers about this problem, and even some hardware vendors decided to incorporate mitigation for this problem in their software. So Intel, AMD, I guess ARM2, something called Intel PLE, pause loop exiting. So to show you what does it mean, what this problem consists of, here's a really nice diagram that I've prepared. So if you know, if you run some application on top of hypervisor usually for whatever reason, people are saying that maybe nowadays it doesn't make sense, but hypervisors are providing virtual CPUs. So they're kind of mapping virtual CPUs to the real CPUs. And now let's imagine that we're running Postgres on top of this system. Now let's imagine like we have a virtual CPU 1, virtual CPU 2, they're like active, and CPU 3 and 4 they're kind of preempted because like they did a lot of job before, for example. And now let's imagine that somehow it happened that whatever backend was running on virtual CPU 2 right now is waiting on the spin log for the result of whatever is going to be performed on the virtual CPU 1. So basically just a normal lock-in situation because database have to maintain consistency and so on, and then it's important. Normally it's not a problem because spin logs are going to be immediately released. It's how they're designed to be used in Postgres, and like it's totally fine in a normal situation. But now let's imagine what happens if hypervisor will decide, okay, Visual CPU 1 got enough time. It got enough work, and now let's preempt it and give some amount of time to work for Virtual CPU 4 that is actually doing something totally different, unrelated, backup, or I don't know, whatever. And what happened here is that what's supposed to be really short amount of time of waiting now, well, who knows how long this Virtual CPU 2 is going to wait, because this Virtual CPU 1 is just like preempted, it doesn't do anything, right? It's up to hypervisor to actually figure out how much is going to be of waiting time or not. And that's where this PLE pause loop exiting kicks in. Basically, PLE detects for you this kind of idle waiting without any progress, and it terminates this waiting by preempting also Visual CPU 2. In the sense that we're not doing this like waiting for nothing, and we, for example, can preempt this one and give some time to Visual CPU 3 to do some actual real work. But obviously, it's a really nice idea, but at the same time, obviously, like there's always pros and cons. This preemption means for us switching to a hypervisor from the guest itself. Yeah, it's like a switching between user space and kernel space. It's also an overhead. So let's try to figure out if we have such kind of situation, how much do we affected by this problem. So to explain you what's going on here, it's actually just a simple experiment. I had some Postgres running inside some KVM, and then there was some pgbench process separately that was generating some workload against the database. The only difference between these two experiments is that the first one was actually running with a default PLE configuration. We see that PLE gap is 128, and in the second situation, we just disabled this feature completely. So to do this, you can just load this KVM intel module with the different parameters, or maybe specify them in your boot mode in the server, and basically you will get these different parameters for your configuration. And then we're profiling again using perf what's going on, what would be the outcome of this experiment. And we see immediately that in the first situation, we actually see quite visible, almost 1 millisecond of a difference in terms of average latencies. It's actually sometimes it could be quite a lot. And what does it mean for us? It means that for this KVM virtual machine, it was so CPU oversaturated, like it was so much saturated and oversubscripted, that PLE functionality was taking some really real waiting spin logs that were waiting for some real stuff for idling, and it was terminating them. Obviously, it means that our real job was like kind of prevented, and we had to do a little bit more extra. That's why we were a bit slower. But it's only like that in this situation. Obviously, this feature was created not for nothing, so you have to figure out on your own whether it's useful for you or not. Okay, here we have to do a little bit of a detour, and I have to explain a little bit how databases normally, like those storage-based databases, are working. Not only Postgres, actually a lot of, many of them are true in general. So what do we have here? Normally we have some different worker process for Postgres. Obviously we run on top of some operating system, in this case Linux. We have some memory allocated in pages, and some storage. So now let's imagine what's going on when we're trying to update some data in our database. So let's imagine that we are trying to update some records, and first of all we're writing this kind of updates into the memory pages, and at the same time we're doing fsync to write ahead log to log these changes. That's just how this stuff worked for recovery and so on. So just remember, these tiny, they're kind of synchronized with write-ahead log, but they're not synchronized with the real storage. So we just logged this. We do not write it so far. So what happened then? After that, background worker kicks in with some particular configuration, like by some delay. Usually, by default, it's 200 milliseconds or something, and tries to synchronize some of the updated dirty pages with a just operating system cache, so not with the storage itself, which is like not durable in the sense that, for example, if some crash will happen, we will not be able to see this synchronized page, but it's like, okay, it's not a purpose of the background worker to synchronize everything. And then the second part is where actually our operating, well, our communication with the outside world kicks in. The point is that Linux kernel by itself, again, based on dirty background ratio, on dirty ratio in general, tries to synchronize whatever it has, whatever dirty pages it has in operating system cache with the storage. Which makes sense because, I mean, it's not possible to keep everything in the cache, right, in the memory. We need to provide this memory for something else, and that's what it's storage for. But it's basically a component that it's totally outside of our Postgres. We cannot think about the Postgres itself when we're not taking into account this part. And then eventually we have a checkpointer that try to synchronize everything with the storage really. So not with the operating system cache, with like everything with the storage. So what we should have to realize from this diagram is basically that when we're talking about Linux, what's important for us is how Linux manages memory and this operating system, basically file cache. So now with taking this into account, let's take a look at the first part of the memory management, in particular at huge pages. Somehow it happened, I don't know why, but in a database world, these huge pages are somehow covered with some mystery around them, and people unfortunately not always understand what are they for, why are they useful, and so on and so forth. So let's try to crack it down. First of all, we're talking here only about classical huge pages, because transparent huge pages, it's in fact not like huge pages by itself. It's just a daemon that runs within a kernel and tries to, from time to time for you in the background, merge some normal pages into huge pages. Usually it actually consumes a lot of CPU and people are advising to disable it. So we're talking only about classical huge pages. So let's try to crack it down. Let's try to figure out whether they're useful for our database or not. First of all, we're going to do the thing that usually people are not doing. We're going to read the documentation. And then we'll figure out that it's like really written there clearly that huge pages are good because they are leading to a less frequent transaction look-aside buffer misses, and those misses are going to be just a little bit faster. So now we have this idea, and how to figure out whether or not it's important for our database. Well, it's straightforward. Let's try to profile for this particular event. Transaction look-aside load and store misses. So here's an example of, again, the very same setup. Well, this time without KVM, so Postgres was just running on the bare metal with some pgbench workload with only one difference. In the first example, we had the huge pages on, and in the second off. And in the meantime, we were recording, as I said before, we have a lot of interesting trace point, and we have also trace point, hardware trace point for transaction look-aside buffers. And we can see immediately that indeed with huge pages enabled, we have almost 20% less load cache misses and about 30% less store misses, which is probably not that important, but nevertheless. And what's important here is that we can see already immediately direct influence of this feature that we enabled or disabled in our service, right? So normally people, when they're doing like a full-scale benchmark, unfortunately, they measure everything from the request to the result, and a lot of the time they see some unrelated noise from different companies they don't really want to measure. And here we just concentrated on one thing. You will get direct result, and then based on this result, we can get, for example, latencies or something. Yep. So so far, what we're talking about could be classified as a stateless profiling, stateless measurement. What does it mean? It means that we basically had some set of events. We somehow were reacting on those events, so we were processing them and so on. And at the same time, but there was nothing in between, right? We were not keeping any state in between of those events. It's useful, but at the same time, what we've got here is something called BPF that totally transformed this picture significantly. So let's talk a little bit about what is a BPF, because I mean it's a really popular stuff nowadays. But just to give a little bit of a perspective. So first of all, BPF by itself with us is since 90s or so, and originally it meant just Berkeley packet filtering. It was basically a functionality when you could create some bytecode, run it within the Linux kernel itself, and attach this bytecode to some functionality, normally for network processing of something, some packages. And it was also totally stateless, in the sense that you would just execute in some bytecode, somehow transform your packet, and then return it again. And then recently what was developed by many actually really cool people. It's something called extended BPF. And it's really funny because nowadays there is a problem in the sense of like naming and stuff. Nowadays people, when we're saying about BPF, they actually mean extended BPF, and original BPF now calls classical BPF, CBPF, which is really confusing, but nevertheless. So what we hear now, we again have the very same bytecode, but now we're able to store some information in between of our events to the registers, tags, and maps. And what is even more mind-blowing, we can attach this stuff. Well, it was actually there before, but that's what gives us superpowers in the sense. Now we can attach this whole system into virtually any function within the kernel or even within the user space itself, which means that we really can execute something for every, for example, visible function within a binary and get some information about this, which is really mind-blowing stuff that changed the pictures completely. Yep. So I have even some demo for that purposes. Let me see what's going on wrong this time. So I hope you can see it. Is it big enough? Okay. Cool. So we have several panes here, several windows, and on this we just have some normal Postgres running in the background with PSQL connected to it. Nothing particularly exciting. So here we're going to do some BPF magic, kind of. So first of all, I have to say kind of obvious thing is that obviously BPF by itself, it's a bytecode. No one is writing bytecode, well, except people from those strange people from Facebook. They're really writing bytecode like manually. I don't understand that. But like we do not, for example, write Java bytecode, right? There are tools that are generating this bytecode for us. And that's exactly the same situation with BPF. There are such tools, for example, like BCC that can already generate some BPF programs for us. And a lot of people are actually using this. So let's try to use this. What is a BCC? BCC is actually it's called BPF compiler collection. Really confusing, but nevertheless it provides us the possibility to write some Python code to generate BPF program. And at the same time, it's already have some interesting, already created, prepared utilities. So let's try it out. So we have something called trace. We can say trace Postgres exec simple query. We have to say it with also with the colon in between. Let's see. Yep. So indeed, now we started to trace some function within the Postgres that we run somewhere else in the background, right? So basically what we're doing, we have some function, relatively publicly visible function, maybe this particular one visible only via the backend symbol, but nevertheless. And what's going on is, for example, we execute some simple query here. We're going to fire this functionality. We're going to find this function being executed from within the application itself and get some information. If we're going, for example, to call it the second time, we're obviously going to see this second time, which is really cool and mind-blowing. But let me show you what's going on in the background here. So, first of all, what BCC does. BCC, it's actually really powerful stuff, but it does pretty simple thing. It generates some C program, which it compiles on the fly via LLVM backend into BPF bytecode. And then it creates also for you in the background some user probe. Well, in this case, it's user probe to attach to. And then BCC by itself for you attaches this BPF program. It's already loaded in the memory and so on. It attaches it to the user probe and then executes something. So let's check it out. There is a BPF tool, really nice thing to see what's going on. So we can see, for example, that we really have some BPF program loaded and registered in the kernel itself. At the same time, we also can see that another really important component, stateful component, map, was also registered within the same program. And here we can see this immediately. That's what makes it so super powerful. We have state in between, right? We can even, basically that's what BCC does for us. We unfortunately will not be able to see, for example, user probes, because user probes are created via perf API, so they're not really visible, for example, via virtual file systems, but nevertheless. So here what we have, but the problem is that, and unfortunately what I've seen some amount of time is that what we're doing here is that like basically we compile some stuff and run with a Python really on the server itself, which could be a problem if you, for example, don't have enough resources or don't you want to install LLVM backend, right? Because we don't want to, for example, bring compiler into our own production service. It's not going to work. And that's why, but the good thing about this stuff is that we can do this, the very same thingy, without even any kind of write subscriber. We can repeat the very same thing by ourselves. And here I'm going to show how is it going to work. So first of all, we have to create a user probe. For that, we can use perf probe -x bin Postgres exec simple query. Yep, and exec simple query return, because we also we actually want to have a user probe for the start function and for the end of the function to get the latency between those two tracing points. We can actually check it out that it was created. There is a really nice file system called tracefs, and there is a file called uprobe. I think it's called profile. Yeah. So here is it created, and we don't have any events yet. So here is actually created, so you can see that we have some function. Here is the offset for this function, and we don't have any events for these trace probes yet. So after that, what we're going to do is we're going to run some BPF programs. So for that, you have to write some C code a little bit. It's, well, maybe sometimes it could be complicated, but nevertheless, I will show you that it's really simple. I already have something here called PG latency. Yep. So we have two parts, user space part and kernel space part, and now we're going to run this stuff. This program, what this program does, it basically repeat the very same that we had before. So it loads BPF program, creates BPF map, and then just watch for this user probe that we've created before to measure the latencies between how much time we spent on this exact simple query. So for example, if we're going to do the very same thing with BPF tool, we see that the very same, we have again our program. We have again created a map, which is a little bit different this time, but nevertheless it also will store our results. The difference is that basically it's a map that consists only of one element, and every time we update this element, we're going to basically update the every information that we have in the map. So now let's do something. Yep. And this program, it's basically repeat into eternal loop and read the very same value from this map over and over again, just to show that it's there. A cool part about this BPF is that there is also a file system called BPFs that we also can mount, and what we can do is that we can actually decouple, which is really nice, we can decouple BPF functionality itself from the functionality of whatever program that is going to read this information from the map. So if you want to check, it's called sys, I think it's kernel BPF, nope, sys, what was that? fs BPF maps, and here is our map. It's really pinned into memory, and we unfortunately cannot read it directly with, for example, CAD or something, but we can write a program that will be able to read it, and it's really nice decoupling. And I have something here called PG latency reader. We can extract this information, and now we can see that this original program stopped executing because there is no value in the map anyway. We just read it and removed it from the original map, which is really nice. And here is an example how it can look like. So we can literally just create a function and see, we're saying please attach this function to this particular user probe and execute something. Absolutely straightforward, nothing particular, with only one trick. The problem is that BPF, when you try to load this program, requires from you an exact Linux kernel version for which this program was created. It's kind of a problem when you want to, for example, distribute these programs, especially, for example, if you want to distribute these programs through, I don't know, Kubernetes cluster or something. There are some different initiative called core, like compile one runs everywhere and stuff, but it's not like there yet, if I understand correctly. And eventually I got tired from this stuff, and what I'm doing right now, I have this, you see, it's hard-coded version of kernel that I kind of was supposed to run it with. I just replace it with xxd, the compiler, disassembler, just literally with set, and it actually works. Why it works, and why is it kind of a safe, is because every time when you load BPF program, it's been checked before by kernel checker, by kernel verifier, which means that if something goes wrong with something is not right in your program, most likely it's going to be rejected. So it's reasonably safe to do this stuff. Yep. And now let's return to our slides. So yeah, that's what I said. We have this BCC program, BCC project, which is really nice, with only one kind of a downside. It's like a common purpose library, and that's why I've created something called Postgres BCC, which is basically the very same thingy, but it contains only those scripts that I found interesting and useful for. They're basically we're concentrating here on the Postgres itself. So let's check how does it work and what do we have in this project, in this repository. This was originally, when I was creating this stuff, was really mind-blowing for me. we can create a BPF program that will, for example, extract less level cache misses per query. So in a simpler situation, we can really get less level cache misses. Normally, it's a metric that we're normally getting just globally per node or something, but we can get literally how much do we get less level caches per query, per update or per select or something. It's really mind-blowing. One can ask, why do we need this? The answer is actually pretty simple. Sometimes we need to understand what kind of memory and misses in general workload do we run. Because, for example, we can in Kubernetes, we can split these different workloads and using different technologies like Intel RDT or something, slice our CPU cache and, for example, say, please, this workload use this cache lines, this workload use this cache lines, and so on and so forth. Another really important stuff is about Writeback, because I've said before, we discussed it before, it's important to understand how Linux manages memory and how Linux manages file system cache. So Writeback is basically this, it's called this process when Linux tries to synchronize everything from file system cache to the storage. And now we understand that we need to get, monitor it somehow. Well, eventually we can do this even with perf, because there is a trace point event for that. And for example, here we can see that, yeah, indeed, at this particular point, kernel was trying to synchronize everything. This one is, by the way, this one is max unsigned long. Because sometimes people are asking me, who is Max Long? It's not a person. So yeah. But the problem is that sometimes it's not enough. The problem is that, for example, when Linux kernel is not being able to keep up with the amount of dirty pages we generate, it does really crazy. Well, not crazy. It makes sense from the kernel point of view, but it's not really nice from business point of view. It injects delays in your backends. Well, that's it basically. We're trying to fight for every millisecond in our queries, but at the same time, when we have such a situation, Linux kernel injects delays, and it's obviously not really nice. And it turns out that it's not that easy to extract this information. That's why I've created another script called Timeout. And this is an example. I was again running some memory-intensive benchmark, relatively modest, but nevertheless. We can see that, for example, for 8 GB of memory, we've got these delays only 4 times. It's not that much, but for bigger servers with, like, I don't know, 128 GB of memory, obviously it could be much more. So you just have to take care about this. Yep, my favorite part, Kubernetes. If you know, for Kubernetes, we have to write such a thing in manifest like resource, request, and limits, and so on. I have actually a separate talk about this stuff. Maybe I will write some blog post about how resource isolation in Kubernetes works, because it's literally hilarious sometimes, but nevertheless. So my first idea, so we have C, for example, we have request and limits memory. The point is that we have in C groups, on top of which basically runs Docker and on top of which runs Kubernetes, we have also something similar. We have soft limit in bytes and hard limit in bytes. And my first idea was, probably they're matched one-to-one. Unfortunately, with Kubernetes, you never know. And it turns out that this one actually does not correspond to anything, literally. It basically, Kubernetes used this parameter to figure out some internal thingies, like, for example, to calculate OM adjust or quality, QoS, quality of service and stuff. So the only thing that we actually see immediately is hard limit in memory. The next idea that I had was also straightforward. It's really cool. Because when we don't have a soft limit, it means that we do not, for example, do page memory claims when we're going over this limit. And of course, page reclaims could be a problem because it's basically an overhead when you're doing something memory intensive. How to prove it? Well, we have to write against eBPF. And in this time, I was totally wrong, unfortunately, because we're doing page reclaims nevertheless, especially when we're doing something memory intensive, and our database container is quite close to the already limited memory consumption. Why we're doing this is basically because we have something called memory pressure, and this memory pressure also calculated per container too, and that's why we're by default already quite close to this limit. Yeah, and that's how can we calculate this stuff. So the last section is about how to run. So I hope that the whole point of this session was not like to give you some information. It's too much of information, unfortunately. Here, you do not have to grasp it immediately, but I really hope that you get interested about this stuff. And I really hope that after this session, you will try it out on your laptop or just in your environment. And that's how you can do this. So if you want to play with this on just your laptop, it's not a problem. You have to just check that those parameters are set up in your kernel. But normally, in all the modern Linux distribution, they're already there, so nothing to worry about. And even the debugfs normally is already mounted. So if you want to run this in the container, it's a little bit more involved. First of all, if you want to do this profiling, you have to don't forget to copy the plugin symbols. For example, in Ubuntu, you can find an Debian by this directory. And also, you have to do not forget that you have to run it with a privileged mode, because all this stuff, unfortunately, requires to write into a trace and debug FS, and that requires privileges. And probably the most of the time I spent trying to figure out how to run it on Kubernetes. Here you already have to provide also two privileged context, but also you have to specify, as I said before, the exact Linux kernel version. So fortunately with BCC there are different environment variables for that, for example BCC Linux version code, and there is also another one called BCC kernel source, which is also important. You have to point it into Linux headers that you're going to install. Yep. And the last part, about how to break it. The point is that what I've just explained is really powerful. It's really super mind-blowing stuff, but you know, with all the with great power comes great responsibility, and that's what we can see here. In fact, when I was trying to do different kind of profiling and stuff, I've seen already in my experience some really nasty situations. For example, in this case, I was trying to figure out how often some particular trigger in a database got fired with some particular information. And then I've created user prop like that to get this parameter from the function. And you know what? There was some extension that was executing the very same function with some null instead of this, with some null pointer. And somehow this was old perf version. It was not being able to cope with it, and it basically crashed the whole backend. So it's obviously not that nice. Another thing that I saw, it also reminds us that stuff that we use, unfortunately, is not without bugs. I was trying to measure how often we do full page writes. And then I was trying to create user prop for that, and somehow that was a bug or something. It was a relatively old version, but nevertheless, perf basically stuck on this stuff. It's stuck on kernel, in the kernel space, in a non-interruptible mode, which means that nothing was able to kill it or stop it, and it was preventing all the other processes from on the very same machine to starting or doing something. Like Docker was not being able to do anything, and unfortunately we had to reinitialize this replica. And the last part is really outdated already. Probably I have to get rid of it, but it's a nice example that we have to be careful. It's like already 2 years old, and it was like Ubuntu with the kernel version 1.04 something, not really up to date. But nevertheless, you can see with this stuff, with Python scripts, BCC is basically a Python, we can trigger kernel panic, which is kind of scary. Fortunately, people are working on that. Nowadays it's relatively straightforward in the sense that it's not breaking anything and it works quite good. But nevertheless, if you want to do this on your production, please, first of all, try to experiment, obviously, on your staging environment. Yep, and at this point, I don't have anything. I hope you have a lot of questions. Yep, please. For what? Mm-hmm. Yeah, it's a good point. There is a nice blog post called easyperf, I think, from one of the Intel employees. And there is a blog post called like how to provide stable numbers or something. And yeah, you're right. If you want to, for example, measure something CPU intensive, so not like with I/O, because I/O by itself it's already pretty fluctuating. But if, for example, you want to measure something mostly CPU related, then you have to put CPU frequency on most performance level. You have to turn off the Intel boost, and you have to turn off also hyper threading, because it also introduces some fluctuations. Yep, please. That's an interesting question. So it depends on what kind of workload are you doing. So by default, if you, for example, want to scale up reads, you just start replicas and it's already by default there, and you don't have to do pretty much anything. For example, with our solutions with PostgreSQL operator and Patron, you just have to update manifest, say, I want to have like 4 replicas instead of 2, and you're fine. If you want to scale up everything, all the workload, like updates and certain stuff, you have to introduce something like sharding, and for that you have to use something like Citus or PostgreSQL, but it comes with all the problems that basically you're aware about sharding and all the complexity that it brings. But it's possible, you just have to set it up, and yeah. Any other questions from those people who are laughing? Any questions? Well, if you will go, for example, to developers part of this project, you will see that there are different categories of contributors. There are core members, committers, and just contributors. So I'm a contributor, and some of my patches starting from 2015, some amount, yeah, they were committed, but not myself personally, because I don't have committing right, of course. So yeah, my code is there, but I was not committing it personally. Any other questions? Yep, I don't see who's sending. Yep. It's etcd normally. But Patroni by itself is good enough because it works with etcd, Zookeeper, and what was this? And console. Yeah. Normally we just run with etcd. Any more unrelated questions? No, it's fine. I mean, I like all the kind of questions.
Is it mandatory to know all this stuff if you work with PostgreSQL production?
Oh, that's a really good question. As I said before, 90% of times, no. Because, well, that's what my colleagues are telling me. Normally, it's like, some people who don't really know how databases are working, they missed some index or created some strange query. That's 90% of the time. But what we have left, about 10% of the time, it's really tricky and complicated. And for example, what we faced recently for the last half a year or something, we were trying to replicate and trying to fix one particular problem in Patroni that was manifesting itself only under the really highly high kind of a load, but only IO load. And solve this problem in conjunction with the Postgres itself without this technique was impossible, unfortunately. So yeah, it's not that often, but those use cases are pretty painful usually. So yeah. Now, what I'm usually saying is that those two approaches, when you do normal like DBA stuff and this profiling, they do not exclude each other. You can pretty much nicely combine both of them. And for example, even I did this already before. For example, even if you created some really strange query, you can still be able to see this from profiles because you see the stack traces and stuff. And obviously, you can fix it as normally, like for example, fixing the schema or something. Yeah, please. Mm-hmm. No, obviously no. In the sense of KVM, you're probably aware that we run on AWS, and all this, unfortunately, hypervisor stuff is hidden from us. So this was just my own personal experiment. But in general, what we're doing, we're trying to go for this right now, and there are this initiative. We're working this right now to do this like continuous, not a profiling, continuously performance testing, let's say it this way. But then, of course, we're checking all those parameters, mostly on the staging environment, and we'll do this kind of invasive stuff only when we know what's going on in production and when it really causes some problems. For example, last Black Friday, I think we had these problems exactly with the shared memory, and there we have to like really do something invasive, but because something was just like down. So, yeah, please. That was my purpose. Well, that's an interesting question. In fact, our team is relatively small. It's like, 7 people or so. Well, I mean, as I said before, this kind of situation when you need to figure out what's going on this level are happening not that often. So for now, it's mostly me and one of my colleagues. And for example, if you go and watch some presentations from Brandon Gregg, who is one of the, well, I guess, people behind this BCC, you will see that he's talking interesting numbers. It's of course approximation, but nevertheless, they're working right now on this, how does it called? BPF trace, I think, project, and it's basically high-level project on top of BCC. So it's like really funny levels. It's BPF trace, BCC, BPF bytecode by itself on the kernel level. And he says interesting stuff that when this project will be perfectly completed and it will be like popular and properly promoted, almost everyone is going to use it. Then approximately like 3,000 people in the world are going to use BCC, and about 100 people are going to write BPF code by itself. So that's level of gradation, apparently. That's how it happens usually. Okay, then if you don't have any other questions, yeah. Can you come again, please? So far, the situations when we have to involve all this profiling are pretty ad hoc. We usually, of course, have the metrics, but they're usually based on what Postgres says us. And all this stuff, we fix problem, and then we remove all this troubleshooting, because obviously it's also an overhead, and we do not want to get this overhead all the time. Yep. Oh, so many questions. I like it. Yeah, I wanted to tell about this. I'm not sure if I have time, but basically the point is that when Alexei Starovoitov is actually one of the developers of BPF, he says from their experience from from Facebook, they run it like pretty much on all the clusters there. Overhead of BPF by itself is like barely 0.3% or something per se. So it's really fast in this sense. But the problems could be when you write some, let's say, slow BPF program by itself, obviously when you do a lot of computation. And for example, in this Postgres BCC, I have a tool to measure latencies for lightweight logs in Postgres. And this one, since it's quite often, it can, for example, take up to 30% sometimes. It depends. As trace, it's also super slow, but people usually aware about this. And perf, yeah, it's reasonably fast, but you have to also take care about that it will not, for example, pollute a lot of disk space, because it have to write a lot of data, and I've seen already situations when it was just taking everything. So yeah, it's reasonable to run it, and for example, people from SysDig, they run it like pretty much everywhere. But yeah, you just have to be aware that there are some corner cases when it's not. Okay, then when there are no questions, you can, if you still have some questions and you're shy enough to ask, you can find me out there. We can talk about the stuff. I have a chess set with me. We can play chess. So, yeah, thank you.